everyone, my name is Anya Abayubi Goodwin, and I am here with my groupmates to present our final performance task, loop week number 4, about total internal reflection, dispersion, refraction, Snell'S law, and Malus'S law. The law of reflection states that the angle of reflection equals the angle of incidence. Whenever we look into a mirror or a squint of sunlight glinting off a lake, we are seeing a reflection. When we look at the text in a book, we are actually seeing the light that is reflected from it. Large telescopes use reflections to form images of stars and other astronomical objects.
In fact, the only way we can see an object that does not itself emit light is if that object reflects light.
The law of reflection is a fundamental principle in physics that states that the angle at which light hits a surface, or known as the angle of incidence, is equal to the angle at which it reflects off that surface, or known as the angle of reflection. This means that when light waves strike a smooth surface, they bounce off at the same angle at which they hit the surface. This principle is what allows us to see reflection in mirrors, shiny surfaces, and bodies of water. The law of reflection is an important concept in optics and is used in many applications such as telescopes, cameras, and microscopes. By using mirror and lenses, we can manipulate the path of light and create images of objects that are too far away or too small to see with the naked eye. In addition, the law of reflection is also used in various industries, such as automotive and aerospace, to design and test reflected surfaces and materials. Overall, the law of reflection is a fundamental principle that helps us understand how light interacts with surfaces and enable us to create and observe images of the world around us. The law of reflection states that the angle of reflection equals the angle of incidence. Incident ray is equal to reflected ray. The angles are measured relative to the perpendicular to the surface at the point where the ray strikes the surface. The law of reflection is a fundamental principle of optics that describes the behavior of light when it is reflected off a surface. According to the law of reflection, the angle of incidence and reflection are equal. In other words, the angle at which a light ray approaches a surface, or the angle of incidence, and the angle at which it reflects off the surface, or the angle of reflection, are equal when the light ray makes contact with the surface. Both angles are measured in relation to the surfaces perpendicular at the point where the ray makes contact with the surface. This law applied to all types of surfaces, including mirrors, smooth surfaces, and even rough surfaces. Light can either be absorbed or reflected when it contacts a surface. It is important to note that the law of reflection only applies to smooth surfaces. Light is scattered widely when it strikes a rough surface, and the angle of reflection differs from the angle of incidence. This phenomenon is also known as diffuse reflection. Let's proceed to the sample problem on the law of reflection. A light ray is incident on a plane mirror at an angle of 30 degrees with the normal. What is the angle of reflection? So for the given is theta I, or angle of incidence, which is equal to 30 degrees. The formula used is theta r is equal to theta I, or angle of reflection, is equal to angle of incidence. So for the solution, we can substitute the given angle of incidence to the formula, which we can see on the PPT. Therefore, the angle of reflection is 30 degrees.
Louis Malus, a French physicist, observed in 1808 that incident sunlight that was reflected off of a glass surface might become polarized. He conducted his experiment using calcite crystal. When viewed through the crystal, light reflected at or near a 57 degrees angle of incidence disappears. After seeing this result, he advanced the idea that S and P polarization made up natural light and that they were perpendicular to one another. As the crystal rotated, the intensity of the reflected light changed from its highest to its minimum. So Malus suggested that the reflected beam's amplitude must be amplitude equals to initial amplitude multiplied by the cosines of theta. Malus, however, squared the amplitude relation to derive the intensity, resulting in a intensity equals to initial intensity cosine squared theta. For the intensity equation, intensity of theta of the reflected polarized light. Here is an example problem relating to this concept. What is the intensity of a laser pointer when using a polarizer? So first, we need to identify the given where the initial intensity is 7.7500155506 watts per meter squared and theta at 30 degrees. Then, we will have to substitute the given into the formula. I is equal to 7.7500155506 watts per meter squared, cosine squared multiplied by 30. Cosine squared multiplied by 30 is the square root of 3 over 2 squared. Then, simplify. Multiply the initial intensity by the simplified form of the square root 3 over 2 squared, which is 3 over 4. So the final answer is 5.81251163 watts per meter squared, or I is equal to 5.81 watts per meter squared. It is crucial if we are to comprehend or learn about the polarization characteristics of light. The Malus'S law contributes in our understanding of the polarizer-analyzer's light intensity relation. These days, this law is employed to clarify the fundamental relationship between optics and electromagnetism and to show the transverse character of electromagnetic waves.
Did you know that Snell's law is important in real life? The formula of Snell's law is used in optical equipment like eyeglasses, contact lenses, and cameras. In this video, you will learn about the Snell's law and the index of refraction. In 1621, Willibrord Snell discovered the law of refraction that later on was named Snell's law. Snell's law defined as the ratio of the sine angle of incidence to the sine of the angle of refraction is constant. Snell's law formula, where sine I is the angle of incidence and sine R is the angle of refraction. The constant value is called the refractive index.
The following is the diagrammatic representation of Snell's law, expressed as n sub 1 sine angle 1 equals n sub 2 sine angle 2. The n sub 1 and n sub 2 are different mediums that will impact the refraction, while angle 1 is the angle of incidence and the angle 2 is the angle of refraction. For the sample problem, if a ray is refracted at an angle of 16 degrees and the refractive index is 1.5, compute the angle of incidence. For given, angle of refraction R is equals to 16 degree, refractive index equals to 1.5, angle of incidence is missing. Snell's law formula, sine I over sine R equals the refraction index. For the solution, sine I over sine 16 is equals to 1.5. Sine I equals 1.5 multiplied by sine 16 is equals to 1.5 by 0.28. I is equals to 0.42.
Total internal reflection. Total internal reflection is complete reflection of a ray of light within a medium, such as water or glass, from the surrounding surfaces back into the medium. The phenomenon occurs if the angle of incidence is greater than a certain limiting angle called the critical angle. Total internal reflection occurs when these two conditions are met. 1. The light is in the more dense medium and approaching the less dense medium. 2. The angle of incidence is greater than the so-called critical angle. As you can see in the figure, when the angle of incidence is equal to the critical angle, the angle of refraction is 90 degrees. And for the total internal reflection, when the angle of incidence is greater than the critical angle, all the light undergoes reflection. Sample problem. An optical fiber made of the glass with refractive index N1 equal to 1.5, which is surrounded by another glass of refractive index N2. Find the refractive index N2 of the cladding such that the critical angle between the two cladding is 80 degrees. For the given critical angle theta equal 80 degrees. Refractive index N1 equal to 1.5, N2 is the one that we are going to solve. And this is the formula. Sin theta equal N2 over N1. For the solution, sin 80 degrees equal N2 over 1.5. We're going to move the sin 80 degrees and N2 equal 1.5 times sin 80 degrees. If we're going to solve that to N2 equal to 1.48.
Brewster's angle, also known as the polarization angle, is named after the Scottish physicist Sir David Brewster. Brewster's angle is an angle of incidence wherein light with a particular polarization is perfectly transmitted through a transparent dielectric surface with no reflection. It states that when an unpolarized light is incident at this angle, the light that is reflected from the mirror or surface is perfectly polarized. For our sample problem, what is the polarizing angle for light that travels from diamond to glass? Since the refractive index for diamond, n equals 2.42, and glass, n equals 1.5 is given, we may now calculate the angle of polarization. The formula for polarization angle is equals to tangent theta p equals to n2 over n1. We will just substitute the given to the formula to come up with the final equation. Theta p, or the polarization angle, is equals to arctangent multiplied to 1.5 over 2.42. Therefore, we can conclude that the polarization for angle that travels from diamond to glass is 31.8 degrees.
So dispersion is defined as the spreading of white light into its full spectrum of wavelengths. More technically, dispersion occurs whenever there is a process that changes the direction of light in a manner that depends on wavelength. Dispersion is a general phenomenon that can occur in any type of wave and always involves wavelength-dependent processes.